So this video is in continuation of my earlier video regarding computation of curvature. So in the last video I said if you have a unit speed curve and it means its tangent vector has length 1, and if you take derivative of the tangent vector, then the derivative vector will be orthogonal to the tangent vector, and this uh, orthogonal vector is multiple of its unit normal vector, that is t dot s is kappa s into normal vector, and if you take the norm of this vector, we get this ks. So this kappa s is curvature of the curve. So if you have a unit speed curve alpha, its derivative alpha dot is the tangent vector, and its double derivative gives you this orthogonal vector, and take norm of that orthogonal vector, that will give you curvature at this point. So here I mentioned some important note. Although the curvature has been computed by using some parameterization, but its value is independent of the choice of particular parameterization. So this curvature kappa s has been defined by starting from this parameterization alpha. So if you have another parameterization alpha dash of the same curve, and find the curvature using this definition, then you will see that the value of curvature is same. And this method, as I have told earlier, that this method is valid for the unit speed parameterization only. So another definition of curvature. Curvature of a parameterized unit speed curve alpha is the magnitude of rate of change of direction of its tangent vector as one moves along the curve. So here I have drawn a curve, and this P is a tangent vector. If you move along the curve, how this tangent vector changes. So tangent vector from here shifted to this point. So direction from phi uh, to phi plus delta phi becomes, so we need to find the rate of change of this direction of phi as we go along this curve. That rate of change of direction of phi with respect to s is called the curvature at the point P. So that is delta phi. So this angle is delta phi, and this length is delta s. So computing this limit delta phi over delta s tend to 0, we get d phi by ds, which is the curvature of this curve. So now I have two different ways to find the curvature. The first way was, we have this parameterization alpha, take its double derivative and find its norm. That will give you the curvature. So first derivative gives the tangent vector, the second derivative is orthogonal to the tangent vector, and the norm of that orthogonal vector is the curvature. In the second definition, now I'm not taking derivative of this parameterization. So here I am taking the derivative of this tangent line, which is making angle phi with the positive direction of x-axis. We are differentiating phi with respect to the arc length s. So this is curvature. So the question arises whether these two definitions are the same. So answer is yes. The both definitions of curvatures are equivalent. So the reader is invited to verify this. So it's not very hard. So one can do it. It is not always easy to find a unit speed parameterization of a given curve, so we need to find a formula of curvature which works for every parameterization and not only for unit speed parameterizations. So till now I have given two different definitions of parameterizations. In both definitions I used unit speed parameterizations. Now I give a new formula which is not wanting any unit speed parameterization. So let alpha be any parameterized curve, say alpha t is xt, yt, and suppose there is a functional relation between this x coordinate and y coordinates. So suppose y equal to fx is functional relation between these two coordinates, then the curvature is given by kappa is take double derivative of f with respect to x divided by 1 plus f dash x square and power 3 by 2. So let's see proof of this fact. So we have given a curve y equal to fx. So I had a parameterized curve alpha, and there is a functional relation between x coordinate and y coordinate. This is that functional relation. And from our previous knowledge of calculus, we know how to calculate length of a curve. So Sx is integral 0 to x 1 plus dy by dx whole square and its square root. This gives me the length of curve from 0 to x. Now take its derivative with respect to x. So if you take derivative with respect to x, the integral and derivatives cancel each other. We get ds by dx is 1 plus f dash x square and whole square root. So from our earlier definition of calculus, we also know that if y equal to fx is a curve, then the derivative f dash x or dy by dx tells me slope of the tangent, and slope of the tangent is that tan phi. So this formula we know from our previous knowledge of calculus. Take derivative of this with respect to x, we get f double dash x is equal to d2y by dx square, and derivative of tan phi is secant square phi into d phi by dx. Secant square phi is 1 plus tan square phi into d phi by dx. So but this tan phi is f dash x, so I have substituted f dash x in place of tan phi. So now d phi by dx is just cross multiplying, I get this, and the formula for curvature is kappa is d phi by ds. Here I have d phi by dx. Now using formula from calculus, I have d phi by ds is same thing as d phi by dx over ds by dx. D phi by dx, go to this previous page, d phi by dx. D phi by dx. From here compute d phi by dx, or from here d phi by dx, or from here d phi by dx is f double dash x divided by this thing. So substitute value of d phi by dx and similarly ds by dx. So we got this formula, which is valid for a curve y equal to fx, or a parameterization in which we know the functional relation between the x coordinate and y coordinate. Corollary to this formula is, suppose you don't know any relation between x coordinate and y coordinate. You have a parameterization alpha whose x coordinate is this xt and y coordinate is yt, and no relation between x and y is known. Then on substituting the values in this formula, we get a new formula which is x dot y double dot minus y dot x double dot over x dot square plus y dot square and its cube. Here x dot is derivative of x with respect to t, and y dot means derivative of y with respect to t, double dot means double derivative with respect to t. So its proof is easy. You can read from the slide. And from these two formulas which I have just given, it is not hard to see curvature can also be defined as, if you have parameterization alpha, take determinant of alpha dot t alpha double dot t divided by alpha dot t cube. And second is take cross product of the vectors alpha dot t and alpha double dot t and divide it by this norm alpha dot t cube. These two formulas are also for computing curvature of any arbitrary parameterization. And again, I say this is not hard to Prove this from the given two formulas which I just gave. So here is one question. So alpha s is r cos s by r sine s by r. So find its curvature. So its derivative is this thing. So from here it is clear that it is a unit speed parameterization, because if you compute its norm, the norm uh, t turns out to be 1. So it's a unit speed parameterization. So it means take its derivative, and the norm of that is the curvature. So this derivative is this thing, and if you take norm, norm is 1 by r, so 1 by r is curvature for this curve. So here now we have parabola y equal to x square. So this formula is not applicable to compute curvature. So we use this formula, k equal to f double dash x over 1 plus f dash x square power 3 by 2. So substituting the values, we get curvature is this. Next is find curvature with a parameterization given by xt equal to 2 cos t, yt equal to sin t, and t lies between 0 to 2 pi. Also find the points where the curvature is maximum or a minimum. So use this formula, uh, k kappa equal to x dot y double dot minus y dot x double dot divided by x dot square plus y dot square cube. So substitute the values, you will get the values of curvature, and the second, it has been asked to find the maximum and minimum value of curvature. So when the denominator is maximum, the curvature is minimum, and the when denominator is minimum, curvature is maximum. So just to find minimum and maximum values of sin t when t lies in this interval.